All right, so this is a file that is going to create a pillow data set. All right, so I've got my NumPy imported. I am importing image from PIL. So even though, again, even though pillow, right, is the package name, the import name is PIL. This is kind of unfortunate because this import name clashes with the original PIL. That's not ideal, right? But if we don't install the original PIL, this won't be a problem. And once again, I have gone ahead and created two iterators. And once again, remember that I know that it takes time to figure this out, right? The first time I did this kind of work, it took me a while to figure these kind of designs out. But this iterator iterates over a given image, and it returns it in patches, right? So if I've got a big image, what this is going to do is break it into little tiles. Now, does handling an image this way make sense for every task? Not at all, right? But it does make sense for some. And I picked it because it will demonstrate a bunch of the stuff that PIL can do. Okay? So what I'm trying to do is break my image into little width by height tiles and build a data set out of them. Okay? So I'm assuming my image is a width by height by channels, right? Image where channels is usually going to be 3. Oh, no, I messed it up. Oh yeah, it's width by height. All right. Oh, no, it's height by width by 3. Good job. So anyway, I've got my current height, and kind of analogously like before, I am going to, while there is enough image left to make a full tile, right? While my current height plus the height of a tile is less than the height of the image, I am going to break that row into tiles, right? So I start with my current W position at 0, and then, while there is enough of my row left to make a complete tile, and this whole thing right here is a Python 2D index, right? So remember that 2D arrays, you index them with the first one and then the second, right? So that's what's happening here. So index for the first, value for the first index, value for the second index, right? So I'm going from cur h to cur h plus height and cur w to cur w plus width, right? And that is going to get me my little 2D tile out of the big 2D array of the image. And then I increment cur w and cur h, right? So that assumes that you're already going to be handed a big height by width by 3 image. This next iterator does the sort of trivial next step of first loading the thing and then converting the patches to floats, right? So it opens the image given by the file name, and we actually don't need this line, remember? Because it does that lazily anyway. And it gets a NumPy array out of the image, and this will automatically close the image, right? I hope you all have seen iterators. I hope you all have seen the width block, right? But the width block will ensure that this image gets closed when we leave this block, right? And then for patch in my patch iterator, so this might be kind of ugly, but one of the nice things about it is that it boxes all that complexity up in here, and that allows me later to just write code that is this simple, right? But so for patch in patch iterator, given that image, we're going to yield that patch converted to float like we did before, and normalize to the range 0 to 1, like we did before. Okay? So we already saw this when we were pre-processing MNIST, right? When we pre-processed CIFAR. It's the same logic, right? Each channel is a uint8 that runs from 0 to 255, and we have to convert that to feed into our network to a float 32 that runs from 0 to 1, right? So we're performing the type conversion, and then we're performing the range normalization, and then we're going to yield that patch, right? And it probably, honestly, would be simpler if I just did all of this in one step right here, but I'm dumb. Okay. So, now that I've defined these two iterators, notice that I'm kind of chaining these two iterators, right? This generator is calling this generator. And while that concept, right here, right, this generator is sort of wrapping around this generator. While that concept might be a little mind-boggling, once you get around it, it makes the code organization very simple, because both of these generators get to be very lean, short, comprehensible, task-specific things, right? So at the end of the day, I can, kind of like I did before, call my images to patches generator, which is this one, ask for a 32 by 32 patch, and I'm going to load fire1.jpg. And I'm going to convert that to a list, right? So again, I got my generator, I'm getting a list. Then I'm going to do it again. I have a fire2.png. I'm going to run the generator on that. I'm going to convert that to a list, and I'm going to add the two. Remember, in Python, list plus list just combines the two lists. So what I have now in fires is a big list of all of the patches from these two images. Okay? And then just like before, I'm converting that big list into a NumPy array. And again, remember, right, that a NumPy array can contain a complex multidimensional thing, right? That's what we talked about with the blobs example, right? Each one of these patches is 32 by 32 by 3, but I can have a NumPy array of these things. It is going to be a k by 32 by 32 by 3 array, right? Where k is however many samples I end up producing out of these two images of fire. All right? So, with all of that done, I then do that with water.jpg. Why do I only have one water.jpg? Because it's bigger. It's just much bigger. That's why. So what do I have? At the end of this, I have a bunch of images of fire, a bunch of little tiles, images of fire, and a bunch of little tiles of images of water, and I'm going to try to train a neural network to tell those apart. So I'm trying to train a network to tell pictures of fire from pictures of water. Again, we'd think this would be fairly doable, right? One of the dumbest reasons this should be doable is that fire is orange and water is blue, usually, right? So when you look at those pixel triplets, if you look at something like this, you would go, all right, that's very red, that's probably fire. Whereas if you see this, oops, that's green. Whereas if you see this, you would say, all right, that's very blue, that's probably water, right? So we would think this wouldn't be hard. Okay, so kind of like we did before, I concatenate my two data sets together, and then I use my repeat and concatenate trick to make a big list of labels, okay? And this time I don't have that cutoff term. I'm not entirely sure how many tiles I get, So I'm going to look at my fires and my waters lists to figure out how many of each label I need. So this is a little different. This time, I'm just going to save these. So notice that the code to make the network is not in here. Okay? So this is another little trick that is useful, might be useful to you as you do your projects. Generating your data might be expensive, right? You might end up with a bunch of memory allocated. It might be an expensive process. It can be useful to put it in its own script, right? So that you generate your data once and then it's generated, right? And you don't have to rerun all of that every time you retrain. So here I'm going to save, right? numpy.save each of those arrays. Notice I don't put an extension here. It will automatically add .npy to whatever name I give it. So I've got fire and water inputs .npy and fire and water labels .npy. And I'm saving inputs and labels there, respectively. So this script uses PIL. It defines an iterator over tiles. It defines an iterator over an image. And then it uses those iterators to break fire and water into tiles. It builds an appropriate list of labels, and then it saves both of those in NumPy files. And it doesn't print anything, so when we run it, bloop, it's just done. It didn't take that long because it's only three images, right? And they're not especially huge. How many images did it produce? Well, so let's see. So 11,000 labels, which means there's probably 11,000 images. I didn't delete fires, so that's what it looks like. And if we look at the shape, the SHASB, come on, we see that there are 3,000 plus a little bit samples that are size 32 by 32 by 3. So square 32 by 32 pixel samples, 3 channels apiece. There's 3,195 of them for fire. How many for waters? 7,800. So that's going to be a problem. Right out of the gate, we see that our classes are not balanced because our water image is so much bigger than our fires image. Fires images, even though there's 2 of them. Okay, now where is it? Oh, I didn't create a stream copy for it. All right. Sorry, forgot to clean up my test code here. All right, that ought to do it. Close enough. Close enough for government work. All right. So here is our code to actually train on this. So I'm np.loading my fire and water data sets. Notice that this time I had to give the npy extension. That's just a little bit of API inconsistency. When it saves it, it wants you to not give it the extension. When it loads it, you have to because it won't assume the .npy is there. So I load my inputs, I load my labels. I have a larger network. Oh, and I forgot to remove the dropouts again. Wah, wah. We'll talk about what those do later. Although the upside is that you're discovering that using dropout is really easy. It's a regularizer. Again, we'll worry about it later. notice, again, these numbers are much bigger. Our first layer is 1,500 units. Why is that? Because our input is 32 by 32 by 3, or 3,000 inputs, right? That's a bit. And there's sort of a limit to how much information we can expect to be able to throw away at each step, right? And as we run this, and again, we're going to hope that my video transcode doesn't explode. Whew, boy, oh boy, right? I guess that's not horrifically slow. So again, we have that slightly alarming sign. I suppose at this point we would expect our loss to be lower than our training set loss or test set loss. But again, I'll go ahead and spoil it for you. At least in my previous testing, this did not, the value loss did not converge. This got bad. We'll see if it does, though. Okay, there we go. So also, it's probably fair to note, and I've done this 4 or 5 times, using softmax and cross entropy for 2 classes might be a little dumb. I feel like those only really matter when you have significantly more than 2, but it's just a habit to get into for any classification problem. There we go. There's a nice big loss, or value loss. So this one, I don't have a really satisfying theoretical answer for why it's not converging. I would expect it to converge because the fire images are mostly orange and the water pictures are mostly blue. And I'm not sure why it's not picking up on that. Not completely sure what the problem is here. I would have to meditate on it for a little bit. That's one of the fun things about this, is that sometimes a problem that seems hard ends up being easy, right? MNIST was pretty easy to train on. Sometimes a problem that seems like it ought to be easy is going to end up being hard. You would think that figuring out, like, learning to tell the difference between mostly orange and mostly blue, you'd expect to be easier than learning to recognize an actual digit, but it kind of turns out that you might be wrong. So yeah, now I would just, oh, that's a huge loss. Look at that. Value loss of 1. Ow. So again, now we would just get to play with this, right? We just get to try different hypotheses about what went wrong. Maybe we could prepare our data differently. We could try different architectures. We could try dropout, which we're not going to introduce for a while, but I had it in there, right? And we would just try to see if we could get this to perform reasonably, right? If we could come up with a theory for why it's not working out well. That is, I think, one of the sort of simple little dark secrets of machine learning is that there's a certain amount of intuition, guess, and check here, right? We can think about what worked before. We can use previous experience as a guide. We can get an intuition for what the networks are probably going to do. And sometimes it just doesn't work, right? There's not a lot of easy theory that you can call on. And there's intuition you can exploit, but your intuition is sometimes going to be wrong. And you're going to end up doing a certain amount of, potentially going to end up doing a certain amount of just manual parameter tuning. All right, so our last value loss was fairly good, but given that our value loss was not stable, I dare not trust it, you know? All right, that is our pillow tutorial. I didn't go over it in great length because a lot of this sort of copies stuff that happened in the sound file stuff, just extrapolated or extended to 2 dimensions for image data, right? Or I guess I should say extended to 3 dimensions for a 2D patch with a 3D structure under it, right? The multi-sample thing. Okay. And again, I'm going to repeat, this kind of thing took me a long time to learn to do. So if you're watching this and you're thinking, oh my gosh, if this is simple, what does he want for a project? don't worry too much, right? I know that this is not simple. This takes time to learn and comprehend and get to work and try. It's going to take a while, right? And some of your projects are not going to want data formatted this way, so you're going to have to think about other ways to do it, right? You're going to have a project that doesn't want tiled image data, and you're going to have to say, okay, how do we want to process our image data, right? So the code that did it didn't make it into the demo, but if you want to, if you have a big corpus of images and you want to shrink them all to 32 by 32, Pillow will do that. It has a resize function, and you can then get a NumPy array out of the resized image. That's not hard to do, fortunately. Okay, all right. So, wanting to give you some last-minute encouragement that, like, I know this is hard to do, right? And I do not expect you to solve these problems as adroitly as I hope I have solved them, right? That would be insane, right? So do not panic yet about your project. I will try to get a list of project ideas soon, okay? Yeah, I think that is that.